All right, y'all. We're gonna get really specific now and dive into details regarding expansion work in various scenarios, and I will define specifically what those various scenarios are. So to start, we have a picture right here of some cylinder containing a gas at some initial state. And you can see in the final state, the gas has expanded and is filling the entire container. So let's first start by defining the gas in the container as the system. Okay. We will also note that there is a constant external pressure from the atmosphere pushing on this gas, so we can think of this container as being open. Okay. And we recognize that external pressure is really from the force of gravity applying onto this area A, right? So, of course, the force is P external times area, or P external equals force divided by area. Either way, right? We could do the algebra. So, after the expansion has completed, and we're not defining how this expansion is being done yet. Maybe it's being heated up, or maybe there's something that's causing it to expand. It doesn't really matter. So it expands here by distance dz. The area has remained the same, so the change in volume of the system, dv, is given by that area times the height that cylinder moved. Okay? So relying on our definition of work being negative force times dz, we can start to plug some of these things in. So we know our force was equal to P external times the area. So let's write that down, and we got to keep the negative sign in there as our convention. So P external times area times dz. And then we also just worked out that area times dz gives us dv. So this is where our equation comes from that I showed you on that previous slide. Okay, so let's box that off. dw equals negative P external times dv. And it's important to note that because here P external is constant, this changes our path function, or I should say this influences our path function. So in other words, we can say now that work, so if I integrate dw, I get w, and then now I've got to integrate this thing, so we'll write integral negative Pex dv, and we're going to integrate that from the initial volume to the final volume. And what we should recognize here is because the external pressure is constant, we can take that outside of the integrand. So that just becomes negative Pex integral from Vi to Vf of dv. And that's a pretty straightforward integral, right? So that's just going to equal negative Pex times delta volume. Okay. And hopefully what we recall from the last slide, right, if we use Pascal and meter cubed, that gives us a joule. However, suppose that we want to use ATM and liters, as is pretty standard units for using ideal gas equation, for example. Well, that's going to give me an ATM liter. That's not going to give me a joule. So we have to use a conversion factor to relate those. Okay, and as it turns out, that conversion factor is related to the definition of a Pascal. Okay, so what we should also note here is working through this further, work is negative Pex, and I'll expand that out, V final minus V initial. For compression, delta V is going to be negative, right? And thus my work done is endothermic. So endothermic work. So in other words, the surroundings are working on the system to compress it. However, for expansion, as we can see, my change in volume will be positive. The final volume will be greater than the initial volume. And because of that negative sign, that's going to give me negative work or exothermic, or in other words, the system is working on the surroundings. If we make a graph out of this thing, just P versus V, we noted that our pressure was constant, right? So it appears out at some constant line and doesn't change. However, our volume went from this initial volume to this final volume. So this shaded region here on this PV diagram represents our work done. That is literally P dV. So that gives us our work. Okay, beautiful. So let's keep going into some different scenarios. So this was scenario number 1, expansion against constant external pressure. So scenario 2, free expansion or expansion into vacuum. Well, work equals 0, so there's no work done when something expands freely into vacuum because there's no opposing external force. So no opposing external force. So work is 0. So that one's easy. Okay. So scenario number 3, isothermal reversible expansion. So this is going to take us a minute to work through. And we want to think about what all of these things mean. So isothermal meaning delta T equals 0. So there's no temperature change when something is isothermal. We also want to think about the thermodynamic definition of reversible. So it's a change that can be reversed by any infinitesimally small variation. So if we imagine like something in thermal equilibrium, so let's say we've got T1 and T2, and we allow that to be separated by a diathermic wall, we know that these temperatures, so the heat will flow from the hot side to the cold side in order to equal these out. And if one side should get hotter than the other, then it's going to reverse. So this will be reversible by some amount dt. Okay. So now when we think about how that relates to our expansion work, when we have something expanding against a constant external pressure, that is irreversible. And it is irreversible, because with that pressure being constant, it's not changing at all to enact the reverse change, right? So this thing that we just worked out with constant external pressure is reversible. So I know this looks really subtle, but by just saying P dV, that turns out to be reversible. And what that means is this pressure is not constant. That pressure is free to change so that we may induce a reversible change. Okay? So for example, let's keep working through this. So now if we were to look at our reversible work, okay, let's write that down, dW equals negative P dV. We recognize here that because pressure is not constant, we have to put in the ideal gas law. Okay, so we know that P equals nRT over V. There you can see it graphed right there. So when we plug that into that integral, we're going to integrate both sides. We get work equals negative integral, and then now I have to plug that in. Okay, so I have to say nRT over V times dV integrated from some initial volume to some final volume. Right? And now, going through this here, we can see that the nRT will be constant. So let's put that out in front, negative nRT. And now we've got integral dV over V from VI to VF. And that's a pretty straightforward integral, just dV over V. That's going to give us a natural log relationship. And so what we get is negative nRT natural log, and applying those limits, it becomes V final over V initial. So this is our isothermal reversible work of an ideal gas. Okay. So, and I'll write that down, ideal gas. Okay, so now you might notice this picture that we have right here. And I want to note here that reversible expansion work is always greater than the irreversible. And we can see that graphically right here. So if we look back to that same example where we had constant external pressure, right? The pressure didn't change from the initial volume to the final volume. So this region right here gives me the irreversible work, just like we drew in that last picture. Okay. Well, when the pressure is free to change to allow the volume to go back from the final state to the initial state, right? Notice here that we're at the same final and initial state. But if I want to reverse this, I can't travel up a constant pressure. I have to increase pressure to compress this thing. So I have to go back this way. So now the region under this curve right here represents my reversible work. But what's important to note is that it also contains all of this area under the curve as well. So the reversible work not only contains the work that had to be done irreversibly, but the work that's done reversibly. So what follows, expansion work is always greater than irreversible expansion work. Okay. So now, what if we wanted to do a van der Waals gas? Okay, so it's not all that different, right? The only difference being is how we integrate this thing. So when we set up this integral, negative integral P dV VI VF, we have to plug in the van der Waals equation into that integral, right? So we'd have to say P equals nRT over V minus NB minus A times N over V all squared. And it's really not that difficult of an integral, right? And I'll put the solution down so we can see. Not a challenging integral at all. So let's just look at the final solution. So that becomes negative nRT natural log of VF over VI. So we still have that same, almost the same. There was one part that I missed, and maybe you might have caught that. Because the volume of our van der Waals gas is not the same as our ideal gas, right? We have to consider that minus NB. So it's VF minus NB over VI minus NB natural log. So very similar to that, but we've got to consider the van der Waals parameter B. And then there's this other chunk that needs to be integrated, and that ends up becoming minus A, N is a constant, so that comes out in front, and 1 over V squared evaluated from V initial to V final just becomes 1 over VF minus 1 over VI. And units are important with this thing, people. So what I want to point out, and then let's box this off really quick. We have two different chunks of this equation right here. So I'm not going to reveal the answer, but I want you to think about what the right units of these are going to be and what we have to do to ensure that we do get the right units. And we'll talk about that in more detail in the live lecture. Okay, I think, yes, that is it for expansion work in the 3 different scenarios. Okay, so there was, let's just review those scenarios, right? Expansion against constant external pressure, free expansion, and isothermal reversible expansion. Okay? All right, I'll see you in the next one.